some of the, actually a couple of properties here, and then a very important theorem about series that I want to mention and discuss. And if we have a couple of infinite series, and for instance, the first one is the sum from n equal 1 to infinity of a sub n's, and that series converges to a, the sum is equal to a, and likewise we have a series of the sum of b sub n's, which also converges and converges to the number b. Then one property is that if we have a series that has a constant c times each of the a sub n's that we see above, then that constant c can be factored outside of the sum. As we see here, the c is factored outside of the sum, and of course the sum was a, and so the result we get here is c times a. So we can create a new series that has a new sum by multiplying each of the terms by some constant c. Likewise, this one would probably not surprise you, but we need to know that it's true. If we take those two series above, and we take the terms of one of them and add or subtract the terms, coinciding terms of the other one, so we create a brand new series by adding or subtracting appropriately one or the other the corresponding terms of each series, then in this case we can actually break that series into two parts. That new series, which would be the sum from n equal 1 to infinity of the terms of the a sub n's, and then either plus or minus one or the other the sum from n equal 1 to infinity of the b sub n's, and so of course we would get a result of a plus b. But we won't use that right away, but there will be a time where we will use it. Next I want to mention a very, very important theorem. Okay, very, very important. Okay, so this is really important, like I said. And the theorem states this, that if we have a series, here indicated by the sum of a sub n's, that converges, if that series converges, then the limit of the terms of the series, so the sequence, the limit of the sequence made up of the terms of the series as n goes to infinity is equal to 0. Now, as you're beginning to delve into mathematics, we have to be real careful, because this is the kind of thing that students misinterpret. And so let me say this. This does not say, okay, let me tell you what it does not say. It doesn't say that if the limit of the a sub n's is 0, then we know the series converges. It does not say that. And that's a big misunderstanding. Whoops, I didn't get it completely closed in, did I? A way that beginning students of mathematics, and although this is Calculus 2, you're a beginning student of mathematics, misinterpret. What it does say, okay, the consequence of this theorem, see that again, it's a consequence, and it's not the theorem directly that seems so important. The consequence is what's called the contrapositive of this, just so that you'll know some mathematical description. It says that if the limit of a sub n's as n approaches infinity is not equal to 0, then the series itself diverges. That's what it tells us. Okay, and so this may be more important. I mean, this representation of the theorem, it's not what the theorem says directly, but this representation of the theorem is how we actually use it. See, if the series converges, then the limit has to be 0. So if the limit's not 0, then the series can't converge, and if it can't converge, then it diverges. And so sometimes this is called this is a test for convergence, or it's really a test for divergence, isn't it? It's really a test for divergence. And in some textbooks, it is actually called the divergence test. Okay, sometimes it's called that. So let's look at an example or a couple of examples how this information can be applied. We'll do that on the next page. Well, in the future, after we get beyond this section and we start looking at all types of different series, we'll have questions that will be something like this. Determine the convergence or divergence of this series. Now, we don't have a way to determine convergence very often at this point. We don't have a lot of tools. But we have one strong tool about divergence. Now, we can have things diverge where this tool doesn't apply. But in this case, and we might be able to look at that and say, what are we doing? We're adding up, when n is 1, we have 2. When n is 2, we have 4. When n is 3, we have 8. So we're taking 2 plus 4 plus 8 plus 16 plus 32 plus 64. That's what this sum is. And it's we're adding larger and larger and larger and larger numbers that are getting unboundedly large. And it's pretty clear that that would not add up to a finite number. It's pretty clear. But in the case that we've got here, this 2 sub n is our a sub n, isn't it? And so when we're wanting to know about the limit of a sub n as n approaches infinity, then we're talking about the limit of 2 to the nth power as n approaches infinity. And it's real clear to us that the limit of 2 to the n as n approaches infinity is in fact infinity. The larger that exponent gets, the larger 2 to the power of that power gets. And so that implies that tells us, because this is not equal to 0, see, it's not equal to 0, then that implies that the series itself must diverge. The only way the series can converge, the only way it can converge, which diverges, the only chance it has of converging is if the limit of the a sub n is 0. And it doesn't say if the limit of the a sub n is 0, then it will converge. But that's the only chance it has of converging. Okay, let's consider it differently. Okay, in this case, consider this series. The sum from n equal 1 to infinity of n factorial divided by 2 times n factorial plus 1. Now, here's what I'm going to do. I'm going to see if I can apply this test. And to apply this test is only going to test for divergence. That's the only thing this test will do, okay? Only tests for divergence. So to test it, we need to consider what a sub n is. And a sub n is this piece right here. So I'm going to look at the limit of a sub n, which is n factorial, divided by 2 times n factorial plus 1 as n goes to infinity. Now, if that limit is 0, then that tells us nothing. If that limit is not 0, then that tells us the series diverges. So here's the way I'm going to determine this limit. This is just an old technique. What I'm going to do is I'm going to multiply the numerator and denominator both by 1 over n factorial. So I'm going to take the result I have here, the limit that I'm considering here, and I'm going to multiply this fraction by 1 over n factorial divided by 1 over n factorial. And then I'm just going to apply some algebraic techniques here. And so when I do that, the numerator up here will be 1, n factorial over n factorial. And the denominator, when I multiply the first term by 1 over n factorial, I'll get 2. And when I multiply the second term by 1 over n factorial, I'll have 1 over n factorial. Now, it's pretty clear, I hope, that when we take the limit of this fraction, well, we look at the limit of the numerator, which is 1. We look at the limit of the denominator, which is the limit of 2 plus 1 over n factorial. That's a factorial there. The limit of 2 is 2, and the limit of 1 over n factorial as n goes to infinity, that's 1 over an ever-increasing and increasing unboundedly denominator, so that limit will be 0. So in fact, we get a limit of 1/2. Well, what's important there? What's important is it's not 0. The only way a series can converge is if the limit is 0. The limit of the terms is 0. And again, it doesn't mean if the limit is 0, it converges, but if it's not 0, it can't converge. And so we conclude then, okay, that this series actually diverges. And that's how we apply this theorem, or actually the consequence or the contrapositive of the theorem. We use it to determine divergence. Before we leave here, well, actually, let me look on the next page to make a comment. And here you see there's a series, the sum of 1 over n's, and this actually, we'll study this much more later. This is called a harmonic series. That's what it's called, and it's a very important series to us in general. Now, we have no reason, well, let me point out to you here. The limit of the a sub n's, say in this case, and the a sub n's are the 1 over n. So the limit of 1 over n as n approaches infinity here is 0. But, and we don't know this, but, you know, we can draw no conclusion from this. We can draw no conclusion about the convergence or divergence of the series. The only way we can make a conclusion is that the limit's not 0. And if the limit's not 0, then it diverges. If the limit of the terms is 0, then it might converge or it might diverge. We don't know. In fact, in this case, and we have no way of knowing this, but I'm telling you, the series diverges. In other words, it has an infinite sum. So, again, knowing the limit of the a sub n's is 0 means nothing. What we said again, and I've repeated it, and I know, but this is important. We said that if the series converges, the limit of the a sub n's has to be 0. But it doesn't tell us if the limit of the a sub n's is 0, that it has to converge. It doesn't say that. And here's an exact example, a perfect example. The limit of the a sub n's is in fact 0, but the series diverges. So knowing the limit's 0, we can't draw a conclusion. Knowing the limit's not 0, we can draw the conclusion that the series diverges. Well, I'd like to look at a couple of problems, classic, application type problems, and not that they're real important, but it's kind of the idea of what goes on with series. So let me state on the next page the first problem, and we'll go through the application or the solving of it, and I think you'll find it interesting. Well, the problem is this. we've got a ball, let's say like a Super Ball, okay, dropped from 6 feet off the ground, off of a hard surface. And the height of each bounce, and when the ball drops, of course it bounces. The height of each bounce is 3/4 of the height of the previous bounce, or the height of the previous distance. Find the total vertical distance traveled by the ball. Okay, so let's think about this. We've got this ball, and we drop it from 6 feet high. Okay, so that's 6 feet. And the ball is going down. Now, as soon as I can't draw on top, as soon as it hits the ground, then it's going to bounce back up, but it's going to bounce 3/4 of the distance that it was dropped from. So the distance of this is 3/4 of 6. Let me write it as 6 times 3/4. And we could calculate that amount, but that's not what I'm interested in right now. Okay. Now, when it gets to the top of this arc, then it's going to come back down, isn't it? And that is the same distance that it traveled up. So here we have, if we add these two together, we'll have another 6 times 3/4. Okay. Okay, now, to make room, I need to come over here. Once it hits the ground, again, then it's going to bounce back up 3/4 of the way, and that may be, I don't know, but we'll say right here. Don't worry about this being precise in looks. So it's bouncing up. Now, what is this? This is 3/4 of what we had before, and so this is 6 times the 3/4 times 3/4 again. So that's 6 times 3/4 squared, isn't it? It's 6 times 3/4 times 3/4. Now what's going to happen is when it gets to the top, it's going to go back down. Okay? And so that's the same distance, which is 6 times 3/4 squared. Now I need to come back way over here. Now that it's hit the ground again, it's going to bounce back up 3/4 of the distance that it just fell. And so that's 3/4 of this amount. So that's this amount times 3/4. So that's 6 times 3/4 cubed. And then it's going to bounce down. I mean, it's going to fall back down. Okay. And so that's distance that is traveled there is the same amount, 6 times 3/4 cubed. Now, let's look here at what we've got. Okay. This amount, 6 times 3/4 plus 6 times 3/4, would you agree that that's the same as 12 times 3/4? And here we have 6 times 3/4 squared plus 6 times 3/4 squared. Would you agree that's 12 times 3/4 squared? And if we look right here, I'm sorry, I had a little senior moment there. If we look right here, this is going to be 12 times 3/4 cubed. And then you can see the next thing we're going to have will be 12 times 3/4 to the 4th power. I mean, this is going to continue, isn't it? It's going to bounce back up, come back down, okay? And it's going to continue that, if you will, forever, isn't it? I mean, obviously, you know, it's not really forever, but the idea is it would be forever. Okay, so let's look at what we have. We can think of, if you will, this amount, 6. Okay, so the very first time it travels, it's traveling down 6 feet. And then it travels up and back down, which is 12 times 3/4. And then we're going to add the next amount, which is 12 times 3/4 squared. And then we're going to add the next amount, which is 12 times 3/4 cubed. And then plus 12 times 3/4 to the 4th power, and this is going to continue, isn't it? Well, try this out. Okay, try this out. Let's take this 6. So the distance then, the distance then is 6 plus. Okay. Think about factoring all of these 12s out. 12 times the sum from n equals 0 to infinity of 3/4 to a power, let's call it n plus 1. So when n is 0, our power is 0 plus 1 or 1, and so we have 3/4. So that's this piece. And then when n is 1, our power is n plus 1 or n plus 1, which is 2. So that's this 3/4, isn't it? So that's our total distance. If you stop and think about that, I think that you'll agree that that's what we would have. Now, we can do a little bit of algebraic work here, and here's what I'm trying to do, is this is really a geometric series that we have here. Let's write 3/4 to the power n plus 1 as 3/4 times 3/4 to the power n. And see, we would add the exponent on 3/4, which is 1, and the exponent on the other 3/4, which is n, we'd get n plus 1. So once we've done that, then we recognize this is a geometric series where this 3/4 is the a value and this 3/4 is the r value. And since this r value that we have, okay, this 3/4 r value that we have is between -1 and +1, then we know that this series converges. And we know what it converges to. See, it converges to a over 1 minus r, doesn't it? That's what we talked about not long ago. So here's what we have then. The total distance traveled is the 6 plus the 12, and the sum of this series is a, which is 3/4, divided by 1 minus r, and r is 3/4. Okay, that is that a over 1 minus r, where r is 3/4 and a is 3/4. Now let's see what we have here then. The denominator, 1 minus 3/4, is 1/4, isn't it? And 3/4 divided by 1/4 is 3. So this ends up being 6 plus 12 times 3. 36 plus 6, or 42 feet, is the total vertical distance this ball will travel if it has the properties we just discussed. Pretty interesting, isn't it? I think this is a fun problem, okay? And this isn't the only way to do it, but this is an application of infinite series. Write the repeated decimal, 0.08, as a fraction in reduced form. Now remember that bar above this, what it really means we have is 0.080808080808. Are you bored yet? Okay, and that's the repeating decimal, so it does that forever. Well, here's an approach. Let's consider looking at this. If we take 0.08 and add to that 0.008, 008. So if we add those two together, we get 0.0808. And to that we add 0.00008. Okay? And we add to that 0.0000008. And if we continue this forever and add all of those together, then what we have is what we started with. That is 0.080808. What have I got here? 0.080808 forever, okay? Or 0.08 repeated, as we say. Well, here's the significance of this then. Let's stop and think what these pieces are. We could write this as 8 over 100, right? That's actually 8 100ths. That's what that is. Okay? And we could write this as 8 over 10,000s, right? This is tens, 100s, 1,000s, 10,000s. So this is 8 over 10,000. Now, let me come over here further. These lines are small, so this is really 8 over 10 squared. And this is the same as 8 over 10 to the fourth. Now, what we have here is 8 over, let's see, tens, hundreds, thousands, 10,000s, 100,000s, 1 millions. So here we have 8 over 1 million, which is the same thing as 8 over 10 to the sixth. And you can guesstimate pretty quickly here that this term is going to be 8 over 10 to the eighth. So here's what we really end up with. Let's see if I can write this in some other way. Now let's do this. 0.08080808 is 8 times 10 to the second, over 10 to the second, plus 8 over 10 to the fourth, plus 8 over 10 to the sixth, plus 8 over 10 to the eighth. That's what we have. Now, let me do one other thing here so that you can see what I'm going to do next. It'll make more sense as I do this next. Let's write this as 8 over 10 to the second, okay, plus. Now let's write this position as 8 over 10 to the second, but multiplied by 1 over 10 to the second. So that's certainly 8 over 10 to the fourth. Let's take this next position, 8 over 10 to the sixth, and let's write it as 8 over 10 to the second times 1 over 10 to the second squared. So that's 1 over 10 to the fourth, and so that we have altogether 8 over 10 to the sixth. And then we're going to write the next position as 8 over 10 to the second times 1 over 10 squared, and that's raised to the third power. So that gives 1 over 10 to the sixth, and that 10 to the sixth times 10 to the second is 10 to the eighth. So we get 8 over 10 to the eighth. And of course, this is continuing forever. Now that ought to look like a geometric series, and in fact it is. If we write that in geometric series form, this is the sum from n equals 0 to infinity of 8 over 10 to the second times 1 over 10 to the second to the power n. Okay? So we do have this geometric series. Now in this case, our a value is 8 over 10 to the second, which of course is 8 over 100. And our r value is the 1 over 10 to the second. See, it's 1 over 10 to the second, which of course is 1 over 100. And so since our r value is between -1 and 1, the way we said this originally is the absolute value of r has to be less than 1. That's another way to say it. but our R value certainly satisfies that, so we know it converges, and it converges to A over 1 minus R. Well, in this case, the A being 8 over 100, and the R being 1 over 100, and what we have is 8 over 100 divided by 99 over 100. And of course, when we invert and multiply, we'll have 8 over 99. And that is reduced. The only factors of 99 are what, 3 and 11? 3 times 3 times 11. And factors of 8, the only factors of 8 are 2 prime factors. So 8 over 99 is the reduced form. And if you check it on your calculator, take 8 and divide by 99, you're going to get 0.0808080808. How cool is that? Well, it's time for you to start on your homework. So we'll continue our discussions about series with some new tests after you do the homework associated with the introduction to series, and particularly geometric and telescoping series. So long for now.